As you said, I'm Andrew Bowman from AbbVie, and I'm going to go ahead and start off by just thanking all the other people who are involved in this work, who are also all co-authors on this. So there's not really going to be another acknowledgement slide toward the back end of this, and I'm going to go ahead and apologize now. This is the only mass spec image that I'm actually going to show in this entire talk. So for all those of you who are here for imaging, you're going to be disappointed. But to give you sort of a background, to put you in sort of the headspace that we were in to be able to do these kinds of experiments, for pharmaceutical industries, understanding of biodistribution is essential to any sort of forward progress. And obviously, whenever you're looking at any sort of biological processes are involving molecular associations and the spatial distribution of molecules. That tissue distribution then is linked to safety, it's linked to metabolism, it's linked to your drug-drug interactions, it's linked to pharmacokinetics, and it's linked to overall pharmacology. So MS imaging then has been a very powerful tool to help determine spatial distribution in tissue. It allows us to do target engagement for both drugs and metabolites of those drugs. It allows us to facilitate assessment of efficacy and safety by relating it with other imaging data, whether that's hepatotoxicity, central nervous system penetration, or tumor spread. It allows us to do biomarker distribution identification and to explore signaling mechanisms. And you have the other advantage that it is a labeling-free technique, which is impossible with most other imaging methods. So for pharma biodistribution studies, what we're looking for are effective drugs that are dosed at low concentration and target a very specific site of action. So monitoring drug progression requires three things. First, specificity to identify our drug and metabolite, high sensitivity for the detection of that metabolite or drug, and high spatial resolution to help us distinguish between different cell types. So high sensitivity at high spatial resolution acquired rapidly for broad molecular classes is sort of the end goal for these kinds of studies. And then sort of to narrow it down even further, the set of experiments I did was really for targeted drug studies. So whenever our pharmacologists come to us and they want us to look at new drug compounds for toxicity or distribution, what they want is subcellular resolution on low-level compounds. And whenever I say that, most of the compounds of interest, if they're going to go to market, are sub-microgram per gram of tissue. And then the understanding of our toxicity and the target engagement are enhanced if we can get down to either single cell resolution or ideally subcellular resolution. And so our current issue is that most of the commercial MS imaging platforms we're using, the sensitivity is not always capable of detecting the molecule of interest at the requested resolution of like 5 to 10 microns. And often it's very borderline. And so for us, any increase in sensitivity at high spatial resolution is advantageous. And that includes up to and including throwing out everything else. And so we're looking to investigate the potential of targeted imaging with multiple reaction monitoring to help us improve sensitivity and expand our MSI utility. And so for that, I had 4 different imaging platforms that I was going to run. The first one that is the one that we're most curious about is a AB-SciX triple quad 6500. This allows us to do MRM studies and allows us to run about 6 pixels per second with 3 MRM reactions per pixel. Attached to that, we're using a MassTech AP-MALDI-QqQ-MRM source. This is currently being run at spatial resolution of about 20 micron, but it is theoretically capable of 5 micron resolution. And then we were operating this in sort of the continuous motion mode. In comparison, we were running the Bruker timsTOF Flex, which you have heard all about just a minute ago. That has a scanning resolution of up to 60K. And we were running this in MS1 mode. This gets up to 30 pixels per second. And we were also running this at about a spatial resolution of 20. Our instrument is capable of getting down to 10 micron. For these experiments, all the data I will show you is with the MALDI-2 laser enabled, because much like you just heard about, MALDI-2 is helpful in enhancing ionization efficiency. And I don't have to describe any of that because that was wonderfully described just a minute ago. We did play around with enabling and disabling the TIM cell in the system to see whether or not we were able to get any sort of improvement in signal to noise for our analytes of interest. And then for those of you who are curious, we're running about 20 laser shots per pixel. We also have still a Bruker Celerix XR7T instrument. This is a scanning resolution between 200 and 400,000, so it would help us by distinguishing our peak with high mass accuracy. This is a significantly slower system though. It's running only about 3 pixels per second, and it's limited to a spatial resolution of about 50 micron. Theoretically, we could get this down to about 20 micron on our particular system, but that is going to involve a bit of oversampling. We're running that with about 50 laser shots per pixel. And then sort of the dark horse candidate for us, this is a Prosolia DESI source that we attached to a Orbitrap Q Exactive. This was also run in a scanning resolution of about 60K. This gets about 5 pixels per second with a spatial resolution of only 200 microns. So significantly larger pixel sizes than we would necessarily want going forward, but this was an opportunity for us to look into the advantages of DESI, which should theoretically have better extraction efficiency. This was used with a Prosolia DESI source that was running about 1,000 microns per second, and we were doing everything in single ion monitoring mode. So for Analyte Selection, within sort of AbbVie, we wanted to provide data for a variety of compound classes. So one of the most important kinds are small molecule drugs. This is phalodipine, which is a commercially available drug. That's about 383 Daltons. We also wanted to look at natural products. This is nicotinamide adenine dinucleotide at about 663 Daltons. We also were looking at antibody drug conjugate payloads. This is monomethyl auristatin E at about 717 Daltons. And we were looking at protein degraders. This is VZ185 at about 994 Daltons. I'll go ahead and tell you now, I'm only going to show you data for 3 of these because the NAD is sort of in progress right now. The other thing we were playing around with was our matrix choice. Since we're using an AP-MALDI source on our triple quad system, AP-MALDI sources do allow us to get a wider variety of matrices because we don't have to necessarily worry about the volatility of the matrix. Right now, I've basically run 3 kinds of DHB related compounds. So actual 2,5-dihydroxybenzoic acid. This is a broadly applied common matrix and it works both in positive and negative mode. We're also looking at 2,6-DHA, which is more volatile and doesn't necessarily last as long whenever running it in vacuum MALDI sources. And potentially this will get us better ionization, specifically in positive mode. And then the last one I was running was the Bruker Flex matrix, which is specific for MALDI-2. And that has an unknown composition, but I can tell you there's something DHB related in there too. To be able to test sort of our limit of detection in these systems, we were using a tissue mimetic model. And so this is sort of built out of work by GSK and then a little bit further work by Lika Lamont at Ron Heron's lab in M4I. And so this is a plastic mold down here into which we were pouring gelatin that creates these 6 sort of pillars. And then those pillars, one of them is round. This is always our blank. And then for this set of experiments, we were running from 10 to 1,000 micrograms per gram of spiked drug in tissue homogenate. In this case, that tissue homogenate was a gram of naive rat liver. And then we included about 5% of drug in solution. The reason we were using a tissue homogenate is that it reproduces the matrix effects of tissue samples. So we can get known concentrations of target. It's highly reproducible. You can transfer this between tissue types, whether you're using liver tissue, intestinal tissue, whatever kind of tissue you would like to run. And then those separated pillars in this particular design allow us to maintain distinct concentrations. And then for the MALDI samples, those were coated with one of the 3 matrices using a TM sprayer. And for sample treatment, once we had acquired a number of pixels, wanted to look at this. And since what we're interested in is the limit of quantitation or the limit of detection, I figured I'd give you an overview of sort of what I did to treat the data to figure out what those limits were. So the limit of the blank is determined as the average signal intensity for that masked channel plus 1.645 times the standard deviation of the blank, and that's commonly accepted as the 90% confidence interval. Once you had the limit of the blank, you add the standard deviation of the lowest concentration, so that for us was 10 micrograms per gram, and you do that same 90% confidence interval. For MALDI, MALDI-2, and DESI, the averages in those standard deviations were calculated in Skills software with 99th percentile hotspot removal on the selected tissue section. The AP-MALDI sources I was not able to load into Skills, so I did a very similar treatment through Excel with the 0 intensity spots removed so that it's also basically where the tissue is. Now, I mentioned that we're really looking at this for high spatial resolution, and I couldn't run everything at the same spatial resolution. So the MALDI FTICR data and the DESI regressions are built on sort of an estimated conversion to a 20 micron pixel size. And I did this by taking the data I collected, dividing the signal intensity by the area ratio, and then dividing the standard deviation by the square root of the area ratio, so that it should be roughly similar to what we expect to see at 20 micron. With all that being said, here's some actual data. So this is for felodipine, and if you look over here in the upper right, you can see this heat map where green is sort of the best we're able to achieve in this matrix, and then as it goes to yellow, then to orange to red, it gets worse and worse and worse. And so for this one, when we're looking at it, our AP-MALDI source is getting us down to about 94 micrograms per gram. The next best source is the MALDI-2, which is running about 245 micrograms per gram as our lower limit of quantitation. That means that for AP-MALDI, we see an increase in sensitivity of 2.6-fold over MALDI-2 and 2.6-fold as well over FTICR, with the DESI source we're using converted down to 20 micron, significantly worse at almost 1,700 micrograms per gram. For MMAE, once again, we were seeing that our AP-MALDI source was giving us the best sensitivity. We're getting down to about 24 micrograms per gram in this case, with MALDI-2 at about 48 micrograms per gram and FTICR at 53. DESI was better than it was for felodipine, but it's still above 800 micrograms per gram. So it's still not getting us to the realm that we want to see. In this case, we were seeing an increase in sensitivity of about 2-fold over MALDI-2 and 2.2-fold over FTICR data. For VZ185, this is the one we were seeing the biggest increase by going to a triple quad system. For the AP-MALDI, we were seeing 11 micrograms per gram as our lower limit of detection. And then the next best thing was the FTICR, which is at 440 micrograms per gram. And then TIMS and MALDI-2 were 1,300 and 2,500, and the DESI was all the way up at 8,400 micrograms per gram as our limit of detection. This means that the AP-MALDI is 118-fold better than MALDI-2, specifically running in TIMS mode, and it's 40-fold better than the FTICR. What this means is that for those of you who are working in a pharmaceutical environment where you're doing very targeted drug analysis studies, an AP-MALDI triple quad platform is perhaps one of the most useful platforms you can have. In terms of sensitivity, the AP-MALDI improves sensitivity over every other platform that we tested, and the targeted analysis displayed a range of 2 to 40-fold better limited detection than anything else. In terms of the speed of acquisition, the MALDI-2 was definitely the fastest system we were running at 30 pixels per second. TIMS was slower at 9, and then our AP-MALDI source is sort of right in the middle at 6 pixels per second, which can be adjusted depending on how long you let your MRM reactions go and how many MRM reactions you do. The DESI system on an overtrap was about 5 pixels per second, and then the FTICR was our slowest at 3. The AP-MALDI source being an ambient analysis means that any sort of matrices that we want to use are going to be much more stable than they would be in vacuum MALDI for long-term projects. And this also allows us to use much more volatile matrices. The DESI platform is also unaffected by the time frame, but since it never approaches the sensitivity of our MALDI platforms, that's not necessarily a big gain. And then in terms of spatial resolution for the 4 platforms that we have, the AP-MALDI source has the smallest potential pixel size at about 5 microns, followed by the timsTOF at 10, the Celerix at 20, and the DESI at about 100 microns. So for us, where we have seen in the past that a single cell is what actually contains our drug, the typical cell size being between 10 and 20 microns means that the only one of these platforms we can run to actually get single cell imaging is that AP-MALDI source. And with that, we do have some ideas for further experimentation. These platforms are capable of much higher spatial resolution, so I do plan to run both the timsTOF and the AP-MALDI source at their limit of resolution. this is also going to include sublimation of the matrix that should improve maybe the coding and the response for all three of the platforms that are MALDI based. I'd also like to increase the matrix choice that we're using here. There are a wide variety of matrices available, and I basically only use things that are DHB or DHB derivatives, and the inclusion of perhaps more volatile matrices can improve the limited detection for AP-MALDI even greater over our other platforms. And I also need to run everything in negative ion mode because all the data I've shown you thus far has been in positive ion mode. But with that, if you have any questions, I'd be happy to take them.
So we have enough time for a couple of questions. Chris.
Sure. Thanks for the talk. I guess I wasn't surprised that the triple quad was that sensitive on that stuff. But did you change the way you were doing any of the FTICR by maybe like doing a CASI window or minimizing the window as well? I won't actually.
Yeah, so I did try a couple of experiments where we looked at more narrow windows to look for these four analytes. Honestly, the improvements we were seeing for our particular things wasn't great. Most of them were chosen because they're not necessarily the best ionizers to begin with, and so the addition of like CASI mode. I haven't tried CASI. That might give us better sensitivity out of that, but we're still running into the issue that the platform might give us more sensitivity, but it's not giving us the spatial resolution that we require.
Right, right. And that's exactly, I get the point about using the AP-MALDI with 5 micron resolution on the triple quad. I guess just as a comparison to it, I don't know if it's kind of apples and oranges on the laser beam size and the probe being volume that you're using, right? You might have charge competition why you're not seeing your drug as much when you're doing a large probe size versus a smaller probe size. Any thoughts on that?
I mean, you're certainly right. There is every possibility that the FTICR is being limited by the fact that I'm not doing like a super narrow window. Whenever I was doing this experiment, I was running, so phalodipine, for instance, runs at about 384. And so I was doing a window between 350 and 400. But that sort of can be narrowed further down, and if I do a single target doing CASI mode, in that I should be able to get a better limit of detection for very difficult compounds. So it's worth us looking into in the future, but I haven't done those experiments yet.
Okay, thanks.
We still have time for 1 or 2 more questions. I have a question. So, so this MRM imaging, especially, of course, you have much better detection limit, and especially for particular compound. So my impression is because it's MSMS, so maybe we have a much low background. So basically, that's why we have a better detection limit.
I mean, that's certainly what we're looking for. So the idea as well for these sorts of experiments is that while we're running them, we're using accurate mass to be able to do MS1 identification for, say, like the timsTOF flex. In comparison, if we're doing MRM mode, we're able to basically say for sure that what we're looking at is our molecule of interest, and then we're removing all the background noise, which is where we're getting our lowest limit of detection, essentially. Theoretically, if we're running this on a different system, maybe a different kind of triple quad, or if we're running it on the timsTOF flex, now that Bruker has announced that you can do MSMS imaging you can do MSMS imaging that might be able to recover some of that distance that we're seeing between the triple quad platform and the timsTOF flex.
So in that context, I imagine if you use ion mobility separation, where then you may minimize some noise level. Have you tried that? Whether that helps at all in TIMS?
I'm sorry, I didn't catch the question.
So in TIMS talk, so ion mobility separation also can be used to lower the noise level, and then may help to lower your detection.
signal intensity, but it was also increasing the overall noise intensity for everything in that same place. So it wasn't actually doing us any good because we weren't separating it away from anything else.
Okay.
So my question goes in that direction. So,
quick question.
oh, sorry.
Please go ahead.
So, so there's a Brian Shade paper in the latest 90s about AP-MALDI. So maybe no one is aware of it. And he said that the activation of a wider mass window increases sensitivity. Maybe that's the clue in this approach, that you are lowering the intensity of the noise because you have a special activation process in the triple quad, which you do not apply in the timsTOFs. So that's my question. You know of the paper?
I don't know that paper in particular. It's entirely possible that if we had some sort of like MRM like or just MS2 information that we were able to do in the timsTOF, that we would be able to improve our limited detection there. I did test trying to do MSMS in the timsTOF, and what I got was depletion of my precursor ion with no gain of any fragments. So yes, I think you're right that if I can do isolation and sort of semi-fragmentation in that platform, I should be able to improve my limited detection for them.
In the wider mass range, and in the triple quad, you maybe already do activation upfront, which you do not do in the timsTOF. So therefore, I would recommend to do some in-source activation. So before you do the isolation,
I'll add it to the list of experiments to run for it.
Okay, we are running behind. I'm sorry. Can you ask him later?
Oh,
after
sure,
the session?
sure.
Yeah.
That's okay. Thank you.
Okay, so we're gonna move to the next speaker, Lillian Alice Gibbings from National Physical Laboratory. She's gonna talk about atmospheric pressure infrared laser ablation